Hey guys, welcome into the Wells Tech Garage for this month's class. Today we're going to be talking about our second episode here of fuel trims, and we're going to be talking about oxygen sensor basics, how they work, how to test them, how to diagnose them, that kind of thing. We're going to be going over the entire oxygen sensor. Now, we're only going to be covering the narrow band oxygen sensor. I'm not going to lie, I got a lot I want to talk about today, and there's just not enough time to get into narrow band and wide band in the same class. So you'll have to join us again next month in March for our wideband sensor class. So today we're talking the narrow band standard oxygen sensor. Now, like I said, I got a lot I want to talk about, so I'm going to just jump right into it. Let's start with the t-shirt giveaway question. For those of you who aren't familiar, we have these t-shirts that we give away every class to anybody who answers our question correctly. So here's the question. Oh, and by the way, to answer the question, just go ahead and chat in underneath the video here with your answer. There's a little chat box. Either give me A, B, C, or D, and if you win, I'd be happy to send you a shirt. So here's our question. ASC style question. Technician A says, when installing a new oxygen sensor, always fill the connector with dielectric grease to prevent water intrusion. Technician B is looking at a Scan Tools live data graph, and he sees his B1S2 oxygen sensor not switching. It's constantly around about 500 millivolts. He says it's failed and in need of replacement. So who's correct? Technician A, Technician B, both technicians, or neither? A, B, C, or D? Go ahead and comment that in, and as we get towards the end of the class, I'll look and see who won t-shirts, and we'll make sure we get those sent out to you guys. So like I said, lots to talk about, so I'm going to jump right into it because I want to have plenty of time to spend looking at our vehicles today. So the narrow band oxygen sensor, again, we're not covering wide bands today, just narrow bands. So rich and lean review. Last month we talked a ton about fuel trims, and rich and lean came up frequently. Now there's this common misconception out in the industry about rich and lean. Rich is commonly thought of as having too much fuel in the system, right? Too much fuel entering into the exhaust system afterwards. And lean is commonly thought of as having too little fuel, but we need to change our mindset on these. We need to rethink these. Rich actually means that we're getting not enough oxygen in the exhaust content. So we're having a lack of oxygen across our O2 sensor. And lean actually means we have an excessive amount of oxygen across our O2 sensor, okay? So thinking about this will vastly help with understanding oxygen sensors. All right, so what is it? An oxygen sensor is a vital input sensor to the PCM. Remember how the computer works: inputs, processing, outputs. An oxygen sensor, a zirconia-style oxygen sensor, is a voltage generating sensor, meaning it creates its own voltage. The sensor doesn't even need to be plugged into anything to create its own voltage. I'll get into how it does that in just a second. In engineering terms, it can be referred to as a galvanic cell or a galvanic battery, and in short it means that it uses a chemical reaction to create an output of energy, in our case voltage. Oxygen sensors first started coming around in the late 70s. Volvo was the first production vehicle to use oxygen sensors, and our oxygen sensors have to be functioning in order for our vehicle to enter into closed loop and begin trimming fuel. All right, so here we have our oxygen sensor at the top, and it reads our exhaust gas. Then it sends its signal out to our PCM. Our PCM then processes that signal and adjusts injector pulse width based on fuel trims, and it can also adjust then spark timing and variable cam timing. That information goes out to our fuel injector. The pulse width is going to depend on the PCM's instruction. That fuel is then sprayed into our cylinder, and a combustion event happens, and then our oxygen sensor reads that combustion event's exhaust. So again, we have inputs, processing, and outputs. So this is our closed loop system. Inputs, processing, outputs in closed loop. Again, this is a closed loop fuel strategy system. So how does it work? Most commonly, we're going to find a zirconia ceramic style oxygen sensor. This is that voltage generating sensor. Now, I had an awesome comment during our last training class asking about this tomato sensor. You know, fruit or vegetable, is it measuring fuel? Is it measuring oxygen? Well, guys, it's just like it sounds. An oxygen sensor is only measuring oxygen, okay? It's not measuring fuel whatsoever. So remember, that rich condition, we have a lack of oxygen across our oxygen sensor. That lean condition, we have an excess of oxygen across our oxygen sensor. Remember, we're measuring oxygen here. So in order to measure that, the sensor will take oxygen that's in the exhaust and compare it through a chemical reaction to its reference air chamber. So to air coming in from the outside, ambient air in our atmosphere, goes into this reference chamber of the oxygen sensor and is compared across this zirconia element, and that is where our voltage comes from, and that's where our reading comes from. So this is all done through a chemical reaction, and it's how the sensor is able to create its own voltage. Again, it's a galvanic cell or galvanic battery. Now, I could get into chemicals and ions and all that stuff and all this chemical reaction transfer, but does it really make a difference to us diagnosing cars? All we need to remember is that it's a comparative style sensor. We have a mixture flowing past our oxygen sensor inside of our exhaust. Our sensor reads the oxygen content in there and compares it against the oxygen content that is in our reference air chamber. So here's a cutaway of a one-wire sensor. So just like this one that's sitting here in front of me, a one-wire sensor. You can see we have our exhaust gas. It enters in down at the tip here. It's got some holes in it that exhaust gas can enter in. Then we have our zirconia style element here. That's this white ceramic part here. And then in the middle there we have this void here. That's our reference air chamber. This contains, roughly 21% or so oxygen depending on conditions in our atmosphere. We're roughly 21%. So this reference air comes from either some holes that are around here on our sensor. Now this is on older style sensors that have these holes. Modern day sensors, the air is actually going to wick down the wire to fill the reference air chamber. All right, and then we also have, again, this is only a single wire sensor, so we have only one output wire to output our voltage signal back to our PCM. So you can see here we have a one-wire O2 sensor, non-heated. So this is important. In order to obtain our chemical reaction, this sensor has to be at least 600 degrees Fahrenheit. Now, when the sensor is 600 degrees Fahrenheit, it's going to read about 450 millivolts at stoichiometric. So a perfect world, 14.7 to 1 mixture, gets burned inside of the cylinder, comes out as exhaust. If everything is perfect, our sensor is going to output 450 millivolts. If everything's not perfect, if our sensor is running, if our mixture is running rich, okay, so we have a lack of oxygen across our sensor, we're going to read a high voltage. About 0.9 or so is going to indicate a rich mixture. And when we're lean, we have excessive oxygen across our sensor. We're going to be reading about 0.1 volts. Now this 600 degrees, it's hard to obtain just by using the exhaust gas. It takes time to get an engine that hot and for the exhaust to get that hot. So we added in we added in heaters into our sensors. These heaters really helped get these sensors up to operating temperature faster and in turn getting our vehicles back into closed loop faster. So this is what really led to our sensors going from 1 or 2 wires all the way up to a 4-wire oxygen sensor. Speaking of that, here is a cutaway of a 4-wire. We still have our exhaust gas coming into the thimble or the tip here. We still have our reference air chamber in the middle of our zirconia ceramic element, but now we have this heater element that's right in the middle here. This heater element is attached to 2 wires. And typically on a 4-wire oxygen sensor, we're going to see those being the same color. This sensor uses 2 white wires to control heater power and heater ground. So this heater is going to turn on, get our sensor nice and hot, and start creating that chemical reaction to create our voltage, which on this sensor goes back to our computer on this nice gray wire right here. And you can also see we have a black wire. That is going to be the ground for the sensor, or the signal ground. Now if you look back on our 1-wire sensor, we were grounding our sensor through the nut of the sensor. Well, how inefficient is that? Rusty exhaust, maybe loose parts, it really is an inefficient ground path. So we added in a ground wire. That's what that black wire is. All right, so on the screen now we have 4 different oxygen sensors with 4 different wiring configurations. Older sensors would typically run a single signal wire, single signal, that's hard to say, a single signal wire and a ground wire, all right? Then we bumped up, we said that ground is inefficient, so we're going to give it a ground wire. So we have signal and we have signal ground. All right, great. Well, our sensors weren't heating up fast enough, so we throw a heater element in it. Now this one can work one of 2 ways. Most commonly we're going to see a signal wire a signal ground wire and a heater power wire, and our heater will get to ground through our action sensor's nut. Now this isn't always how it's going to work. There are some sensors out there that are going to be signal. It's going to have signal here. It's going to have a heater power and a heater ground wire, and then our signal will be grounded back through the nut. But again, that's not as common as the first way. And then we get to the 4-wire sensor, and this is what almost all of our action sensors are nowadays. They have signal, signal ground, heater power, and heater ground. And again, most of the time those heater circuit wires are going to be the same color. On our other sensor there, they were white, they can be gray, whatever. They're typically going to be the same exact color. All right. So we have another type of oxygen sensor. Now this one's not nearly as common as the zirconia style. It was used on old Chrysler and Jeep products, but it never really caught on. The zirconia element sensors really is what took over oxygen sensors. A titania style sensor does not generate any voltage. Instead, it changes resistance in response to the oxygen content inside of the exhaust. What it does is the computer sends a small load to the sensor, and based on the voltage drop across the sensor, it determines whether it's rich or lean. Now this operates a little bit, I guess I would call it opposite of our zirconia sensor. When we have high resistance, remember with our zirconia we had high voltage, it indicated rich. Well, with a titania sensor, if we have high resistance, we have a lean condition. If we have low resistance, we have a rich condition. So we're talking resistance and voltage, but they do operate opposite between the two sensors. So zirconia, high voltage, rich condition, low voltage, lean condition. Titania sensors, high resistance, lean condition, low resistance, rich condition. There is a benefit to titania style sensors. They don't require that reference air chamber. They have nothing that they have to compare to. So they're great for people who are doing off-roading and that kind of thing because there's no way to get that reference air chamber all plugged up and not functioning on there. Okay. Front and rear oxygen sensors. Now, on a lot of our modern day vehicles, we're seeing multiple oxygen sensors, anywhere from 1 to 2 to 3 to 4, even vehicles with 5 or 6 different oxygen sensors on the vehicle. Typically, we should see our front oxygen sensors, our frontmost sensors, are going to be our switching sensors. These things should be switching back and forth rapidly. Our rear oxygen sensors will really depend on the manufacturer, but typically, typically we're going to see a much slower switching rate on these rear sensors, or possibly even a flat line across. Fast or even identical switching to the front sensor can indicate a bad catalytic converter, but again, you always want to look at your code set criteria to verify that. Some rear O2 sensors are only used for cat monitoring and can be referred to as cat monitors, while other rear O2 sensors are actually used to help with fuel trims. So it really depends on the vehicle. Again, look at your code set criteria and your oxygen sensor circuit and component descriptions. The computer typically will monitor the rear O2 sensor and compare it to the front to determine catalytic converter efficiency. So again, just like that example there, if both sensors are switching at the same time, the same rate, chances are your catalytic converter isn't doing any sort of chemical reaction inside of it. If you have a front switching sensor and a nice steady back sensor, chances are your CAD is working just fine. There's parameters and test conditions involved. Again, look at your code set criteria and circuit descriptions. All right, so here is where it gets a little bit dicey. Just stick with me because we're going to be talking about the way an oxygen sensor reacts and how the PCM reads it. Now I have some awesome graphs and stuff involved here, so just stick with me. It gets a little bit wordy at this part. So again, remember an oxygen sensor is just an input sensor. It reports back to the computer what is happening inside of that exhaust. All right, by nature, an oxygen sensor, 1 wire, 4 wires, doesn't matter. A zirconia style oxygen sensor does not switch between that 0.1 and 0.9 by nature. If you have, let's say you get a propane torch out, okay? And you heat up this sensor and you hit 600 degrees and you just hold it on there, hook a voltmeter up to this thing, you're going to start reading voltage. And depending on the air-fuel ratio of your propane torch will depend on what you'll read across this sensor. It doesn't have to be plugged in, and it's not going to switch. The switching actually happens from the PCM. The PCM is what makes the sensor switch. And this happens for 2 reasons. Reason number one is it helps to keep the cat efficient. So the cat's able to get the proper amount of hydrocarbons and oxygen in order to create its own chemical reaction. The other reason is because an oxygen sensor is only reliable at that stoichiometric 450 millivolt mark. If it goes rich or lean, the computer doesn't understand how rich or how lean. So say we hook a voltmeter up to this thing and it's reading 790 millivolts coming out of the sensor. What does that mean? The computer doesn't know if that's an 8-to-1 mixture or a 2-to-1 mixture. It just knows that the sensor is running rich. Same thing with lean. If it's running at 222 millivolts, the computer doesn't know if it's running 16 or 18 or 22 to 1. It has no idea. All it knows is that it's running lean. And this is why nowadays we have our wideband and our air-fuel ratio sensors. But again, we're getting into that in the next class, so be patient. So the way that the computer figures all this out is by adding and subtracting on the short-term fuel trims. Its priority is to watch the 450 millivolt mark. Now, it watches our voltage marks as well, but it's typically monitoring those for an overvoltage concern or a stuck high or stuck low style code. But its priority, again, is to watch that 450 mark. So just stick with me. The PCM monitors that 450 mark and watches for the signal to cross that mark, okay? So this is what is called Pcm Cross Counts, okay? Think of that 450 millivolts in there. Think of that as a switch. Now, don't get me wrong, there's not some switch inside the PCM that the signal is opening and closing, but just think of it that way. It helps me to visualize this. So, okay, the PCM says, all right, I'm running lean right now. I need to richen this mixture and try and get this switch to open. So our signal is lean, it's down around 100 millivolts. I'm going to richen until, boom, I hit that 450, I'm going to open the switch. All right? So our computer is now running, our mixer is now running rich. The computer's happy. It says, okay, I just saw us go rich. I have no idea how rich. Let's subtract on the fuel trims until I get us to run back lean. All right? So we're gonna subtract fuel trims and boom, we cross the 450 mark, we maybe close that imaginary switch, and the computer's happy. It just saw it go lean. So it's able to determine how rich or how lean it is by adjusting the short-term fuel trims. And here, let me show you exactly how that works. All right, so on our graph right here, we have a perfectly running engine, okay? We have nice oxygen sensor switching. We're looking at roughly 2 seconds here. Again, this is just drawn out. This isn't off of a lab scope or anything. I just want you guys to understand this. So our scan tool right now is going to read short-term +1. So our sensor right here was reading lean, okay? Our computer knows that it's lean. It's below its 450 millivolt switch. Again, it's not a switch in there, but just use that in your imagination. So we're running lean. So the computer says, okay, I know I'm lean. I want this thing to cross 450 and run rich. All right? So it adds 1 to the short-term fuel trim. Bingo. Crosses 450. The computer says, great. I just went from lean to rich. I saw our switch. I know I'm capable of doing that by adding 1 to our short-term fuel trim. So what am I going to do? I'm going to now take 1 away. So we're up here. The computer says, okay, great. Let's take that 1 away, and boom, right across the 450 mark again. We trip that switch. The computer says, great, I just went lean. That's awesome. I know I'm able to run lean by taking away 1 on our short term. So let's do it again. We go up. The computer adds 1 to our short term. We cross the 450 mark. Again, we cross that switch. Great. The computer's happy. It saw it go rich by adding 1 to our short term. And same thing again. We take 1 away from our short term. We add 1. We take 1 away. Now again, this is a perfect running engine. Chances are you'll never see it be +1, -1. But you will see this happen back and forth. You'll see your short-term fuel trims and your oxygen sensors react almost the same. And I'm hoping if everything happens right on the GTO, I'll be able to show you guys and demonstrate this real time on our GTO in just a couple minutes. So what you would see if you were graphing your short-term fuel trims over your oxygen sensor, you would see it, you know, oxygen sensors running lean. All right, we're adding 1 to our short term. Boom, it crosses 450. The computer says, great, I just saw this happen. Let's take that short term away. Let's take 1 away and make that sensor run lean and rich and lean and rich. And the reason why this happens like this and it looks like this is because this takes time. Again, we're in our closed loop. So our oxygen sensor reports, the computer processes, adjusts the pulse width of the injector. Oxygen sensor reports, computer processes, adjusts the pulse width of the injector, reports, processes, adjust the pulse width. So inputs, processing, outputs. Again, closed loop. It takes time to do. This can't happen instantly. So this is how the computer is able to determine rich or lean and where exactly the mixture is, how rich or how lean, depending on what it has to do with the short term. So let's say that there's a problem. Let's say that we have here. Let's say we have a perfectly running engine, things switching back and forth. We're going between -1 and +1. Everything is happy. Everybody's happy. The computer says, we're running great. I don't have to set a check engine light. I'm doing just fine. All right, but then we introduce a small vacuum leak into this thing. So what does the computer do? It sees our mixture is lean, all right? It crossed that 450 mark and it went lean. What do we have to do? We got to add 1 to our short term, right? But we added this 1 to the short term right here, but we didn't bring it back across 450. It hasn't switched yet. We haven't gone rich. The computer hasn't seen that switch. Okay, so what does it do? Adds another 1. So now we're short term +2. But we still haven't seen the computer switch. We haven't seen the oxygen sensor switch. We're still pegged lean on our oxygen sensor. So what do? We got to add another 1. Short term +3. Still, our oxygen sensor is still pegged lean. We're getting too much oxygen across our sensor. So what are we going to do? We're going to add more. +4. All right, so we're at 4 positive short term. Boom, our oxygen sensor switched, right? We crossed the 450 mark. The computer's happy. It says, I just added +4 on our short-term fuel trim, and I made the oxygen sensor switch. Awesome. That's great. I just saw it go rich. Now, let's make it go back lean. So the computer takes 1 away. So now we're at a short-term +3. We took 1 away, and boom, it switched back to lean right away. Okay, great. Now this is where the computer begins to learn, and it's going to make a difference on what vehicle you're working on and what computer you're working on, but this is where you should start to see learning. The computer should say, all right, I was up to a +4, I took 1 away, I went back lean, so I must have to add fuel. This is where the long-term fuel trims start to react, and again, I'm really hoping if everything works out right that I can show you guys this real time. So we'll see our oxygen sensors start to raise up and our short terms are going to start to come down. And eventually what's going to happen here is we're going to see our long terms ratchet up to that +3 mark. So they're going to sit right at +3 and our O2 sensor is going to go back to being happy, switching between +1 and -1. If you remember from last class, I talked about our long-term fuel trim's goal is to satisfy our short-term fuel trims, okay? So in this vehicle, to satisfy our short terms and bring them back to this happy switching like we're seeing right here, we have to see a long term of a +3 and our short term switching between the +1 and the -1. And again, I have the GTO all set up. I hopefully, if everything goes right, we'll be able to show you guys real time the fuel trim reaction to the way the oxygen sensors are working. All right. Now I want to just talk a little bit on installation of oxygen sensors, the do's and the don'ts. Obviously verify the oxygen sensor is the same as the one you just took out. Make sure the connector is the same, that kind of thing. When you take the old one out, oxygen sensors get rusty, corroded. They can be a pain in the butt to take out. Verify that the threads of the sensor, the threads of the oxygen sensor bung of the hole in the pipe, make sure that they're okay. You can get yourself a thread chaser for a pretty cheap price if you have to. And even if it just makes you feel better, go ahead and chase out that hole. Make sure the threads are okay so when you thread in your new one, you don't run into any problems. I mean, these sensors sitting here only have a couple threads. I'm looking at this one, I see 4 layers of threads here. This one the same way. There's not a lot of threads on these things. If you cross-thread them, you can run into issues. And also, you can create a false lean concern. If you cross-thread this thing, it doesn't get down tight, you're going to be bringing in air from the outside into the exhaust pipe at the oxygen sensor, and it's going to throw off the oxygen content in the exhaust versus the oxygen content in the reference chamber. All right? So make sure you tighten the sensor down and it's not cross-threaded. Use an oxygen sensor socket or wrench. This is important. Obviously, all of our sensors have wires coming out of the top of them, right? So in order to tighten this thing down, they make a special socket. You can't just throw a deep well over this and crush our wire, or it's not going to respond properly. So they make a socket with a cutout on the side that you would put over this, and the wires can hang out of the side, and you can tighten this thing down with a ratchet. Now when you're tightening this down, it's important to not plug in the connector until the sensor's tight. If you plug this thing in and it's tethered like it's supposed to be, and you start turning the sensor in, every turn you're going to start twisting this wire, and you could eventually wreck it and cause problems with the wiring harness. So thread your sensor into the hole first, get it nice and tight, then plug in the connector. All right, this one's important. Apply a small dab of anti-seize to the threads. Anti-seize will kill your sensor. If you get it all over the thimble and the tip here, it'll kill the sensor. It won't react properly. Small dab on the threads. But most sensors now, when I pulled these two out of the box, these are brand new sensors, they both have anti-seize already applied to the tip because people were over applying. So more is not better. Don't take and apply more anti-seize to this. If it already is applied, just go with it, install it, you'll be just fine. Don't apply more. All right, lastly, keep the sensor clean and the connector clean, especially in rural settings with dirt roads, or for you off-roader guys, you don't want to plug up that reference air chamber. It needs to be able to get fresh air from the atmosphere into the sensor. All right, some don'ts. Don't drop the sensor, don't hit it with a hammer, don't hit it with a wrench, you know, that kind of thing. If you're trying to take one sensor out, you know, don't go pounding on a wrench with a hammer to break it loose. This thing has ceramic inside. You wouldn't do that to a spark plug, right? You could crack that ceramic. You could do the same thing to your oxygen sensor. You don't want to crack it. If you were to crack it, you might not even see. You know, this whole sensor is covered in a metal body. You might not even see that it's cracked, but it might not work right. What can happen is if you crack the ceramic here, I'm going to back up here. I'm going to go back to our other image. Here we go. If you crack this ceramic right here, you know, let's say you put a crack in it right there, the exhaust gas can then flood into our reference chamber and fill our reference chamber with exhaust gas. So now what is the sensor comparing? It's comparing exhaust gas against exhaust gas. There's not going to be any reading. It's gonna give you a skewed reading, all because you dropped the sensor and it's now cracked. Okay? So be careful with these. These can be fragile. You know, you wouldn't drop a PCM and install it in a vehicle, right? I mean, most new PCMs, right on the case of the PCM, says scrap if dropped. So be careful with oxygen sensors. They can be damaged by dropping them or hitting them with a hammer or something like that. All right, again, don't glob the thing full of anti-seize. I just talked about that. It can kill the sensor. All right, this next one here is something that I am guilty of, and I'm sure many of you are too. Do not apply dielectric grease into the connector. All right, now this, I have a hard time with this because like every connection on a vehicle, I want to put a dab of it in there because I want to, you know, just make sure that I have a nice watertight connection that doesn't allow any contamination in there. But what you could have just done is you could have just blocked that reference air chamber's air path. Like I said before, our reference air actually wicks through the wiring between the wire and the sheathing around it. You know, this is an old style single wire sensor. It's got no air intake ports on the back of the sensor here. The air comes through the wiring of the sensor. Now these sensors do have weather pack seals, so you should never have to worry about it. If you put this connector together dry and clean, you know, with the connector that's on the vehicle, you plug these things in together, as long as they're clean and dry when you plug them in, they should remain that way unless you've damaged the weather pack seal, okay? Maybe if you back probed and you put a hole in the weather pack seal or something, that could create damage in there. By applying dielectric grease into this connector, you could block the path for that reference air to flow into the chamber, all right? So keep that in mind. That can create some sort of weird issues on your oxygen sensor, so maybe lack of response or something like that, issues on your oxygen sensor if you go ahead and fill that thing up with dielectric grease. All right, and lastly, this is kind of something that happened back in the day. Don't go ahead and undercoat the whole underbody of your car, go right over your sensors and your exhaust. Back in the day, this would plug up the reference ports on the sensor. It could still plug up the reference ports on the wire, but it would plug up the reference air ports on the sensor, and obviously our sensor's getting hot, it's going to burn that stuff off, it's going to smell, it could create smoke, or it could create other problems. So when you're undercoating your vehicle, be careful, don't spray the sensors. All right, sensor failures. Let's get into what causes an oxygen sensor to fail. Well, silicone poisoning is very common. You pull the sensor out, and the tip of it will be covered in like a white powdery substance. This is because of any sort of sealer that you're using on your crankcase. It needs to be oxygen sensor safe or sensor safe sealer. So timing cover gaskets, valve cover gaskets, intake gaskets, anything that you're using RTV like silicone or whatever on, make sure it's labeled as sensor safe, because those fumes will then get into the crankcase, they'll get into the combustion chamber, they'll flow past the oxygen sensor, contaminate it, and create a skewed reading on the sensor. Then we have oil contamination. Two different ways here. Burning of oil can create a fouled type sensor, just like a fouled spark plug. It can create issues with that, giving you a dark color on the sensor, maybe a sooty tip on the sensor, something like that. But external oil leaks, this is something that's often overlooked. So let's say you have a vehicle, they got a bad valve cover gasket, okay, it's leaking a little bit of oil over time, but every 2 months you seem to be putting in a new oxygen sensor, right? The darn thing just keeps failing, it must be the part, right? Well, there's a possibility that that oil is seeping its way into the sensor and getting into the reference air chamber, okay? Remember, these sensors want to be clean and dry to be able to get that air into them, and if you cover the thing in oil, chances are it can seep its way in and create issues. All right, antifreeze, burning coolant. Typically will give you a green tip on your oxygen sensor, and this is going to happen, you know, if you have a head gasket or maybe an intake gasket problem, something like that. And this is where I want to talk about the complete repair and, you know, the CYA, the cover your, you guys know. If you have a head gasket problem on a car, chances are your oxygen sensors are contaminated. At the very least, pull them out, verify that the tips are nice and clean, you know, they're not covered in green. If they are covered in green, at that point you probably want to recommend them to your customer. Not only to get the vehicle back to running good, but it's going to keep them from coming back in, I don't know, 200 miles with a check engine light for a slow response code on their O2 sensor. So keep that in mind, the complete repair, the CYA of the mechanic world. Let's not try and create any comebacks. Physical damage, I talked about that already. Fuel contamination, dark and sooty, just like a fouled out spark plug. You know, if you got an injector that's sticking open, the engine's running excessively rich, that kind of thing. Fuel contamination, you'll see dark and sooty at the tip. Dielectric grease we talked about. Wiring damage and corrosion, just like any wire on a vehicle, inspect it for any damage to the wire, to the sheathing on the wire, or corrosion on the wire. And then age damages sensors. These sensors don't last forever. They're sitting in a caustic environment. They're sitting in exhaust gas all day, every day. Eventually, they will wear out. I wouldn't maybe call them a maintenance item. I wouldn't be selling them with that 100,000 mile spark plug job, but it might be something to think about for your customer who's really maybe complaining of a lack of fuel economy or something like that. Check out those oxygen sensors. Now we can get to diagnostics. We understand how the sensors work. We understand what the PCM is doing with them and to them. We can talk about diagnostics, but before I get to the vehicles, I have our GTO in here, and I also have an O2 Mazda Tribute in here. I just want to talk a little bit about diagnosing oxygen sensors. So here we have some O2 sensor codes. A P030 is an HO2S heated oxygen sensor. B1S1 heater control circuit malfunction, B1S2, B1S1, you know, all these numbers are being thrown around in acronyms. But here we got, you know, a couple codes. Here's some more. And some more. And finally the end. That is 62 total OBD2 mandated specific oxygen sensor related codes. Now this is not including manufacturer specific codes. This is only 62 of the OBD2 compliant oxygen sensor codes. So between P0 and P1000, there's 62 codes just related to the oxygen sensors on the vehicles. Now this is important, and I'm going to get to it here in just a minute. But first, what does the B1 and the B2 stand for? B is for bank, bank 1, bank 2. On a 4-cylinder car, and I'm talking inline 4, you're going to see that sensor referred to as bank 1. If you have like a boxer motor or something like that, you might have two sensors, bank 1 and bank 2. A V6, a V8, you're going to have bank 1 and bank 2 if it's that style of vehicle. Now, if you head out to our website, if you're not sure what side is bank 1 and what side is bank 2 in your vehicle, head out to our website, wellsve.com, click on the search parts catalog option, enter in your vehicle's information, and select firing order, and we've done all the work for you guys. So I went and did that. I went to the website, entered in 06 F-150 5.4, went to firing order, selected truck, 5.4 liter, hit view, and you can see here we got a nice little picture of a truck, and it says 97 to 01 Ford, 5.4 liter. It's a coil on plug ignition, and we have our 1, 2, 3, 4, 5, 6, 7, 8. These are our cylinders. Bank 1 is always going to contain cylinder 1. So on this vehicle, bank 1 is going to be on the right side or the passenger side, and bank 2 is going to be on the driver's side or the left side. All right, so 5, 6, 7, and 8, bank 2, the driver's side. We also include the firing order on there, and that's wellsve.com. Search parts catalog, enter in your vehicle's information and select firing order. Now this is also super helpful, just as a little side tip, for if you're looking at misfire problems, right? So you get a P0302, okay? You got a misfire on cylinder 2, right? Well, if you're working on a Ford or if you're working on a Chevy, you might not know where exactly cylinder 2 is. They're going to vary. On a Ford, cylinder 2 actually happens to be most of the time on bank 1, right after cylinder 1. Where on a GM product, you might find that cylinder 2 as being the first cylinder on bank 2, okay? So this kind of thing is going to change, so it can become super helpful for misfire diagnostics as well and just locating cylinders. So again, we've done all that work for you. This is available out on our website at no charge to you. And we're constantly keeping it updated. You know, every model year when information becomes available, we like to keep this thing updated for you guys. So just another little freebie that we give you guys. Okay, so I got some little infographics here talking about this S1 or S2. You know, S relates to sensor and sensor location. So S1 is always going to be somewhere between the exhaust manifold on the engine and the catalytic converter, okay? It's going to be the pre-sensor, or sometimes referred to as the pre-cat sensor, but S1 is always going to be before the cat. So you can see bank 1, sensor 1, we have a 4-cylinder. This is bank 1, sensor 1, and bank 1, sensor 2 is always going to be post-cat. Now we get into some weird engines, the 3.1, 3.4, 3.8 GM motors with the crossover pipe. They're only running 2 oxygen sensors on a V6 engine. You have bank 1, sensor 1, bank 1, sensor 2. What's unique about these engines is the fact that they are unable to trim fuel trims for each individual bank. You know, it's a V engine, it's got bank 1, it's got bank 2, but it only uses 2 oxygen sensors. That bank 1, sensor 1 right here is monitoring both banks at the same time. It's only able to trim fuel for the engine as a whole, not like something like this. So in something like this, we have bank 1, sensor 1, bank 1, sensor 2, bank 2, sensor 1, and bank 2, sensor 2. This engine is able to trim fuel trims independently of either side. So we have a bank 1 issue, maybe we have an injector issue on bank 1. It's going to be able to change those fuel trims specifically on bank 1. And bank 2 will be unchanged. And then also we have bank 1, sensor 3. This is going to be the rearmost sensor on a vehicle. Sensor 3 will always be rearmost. And bank 1, sensor 3. And then some vehicles that run 6 sensors, you'll see bank 2, sensor 3 there also. Now, an interesting tidbit of information here is there's certain vehicles out there that are using like an ion sense type ignition system or something where they're able to monitor each cylinder individually. Those type of vehicles can monitor and correct fuel trims individually for each cylinder on the engine. So I would assume as we get more technical with our engines, as they get more advanced, we're going to start to be able to see vehicles able to trim fuel for each individual cylinder. And think of how much more efficient that can make a motor. You know, in this instance, if we have a cylinder 3, say our injector's plugged up on cylinder 3, what is that going to do? It's going to say, okay, my first sensor's running lean. I'm getting too much oxygen past it because I'm misfiring here. I don't have any fuel coming out of cylinder 3 right now. I'm running lean. So what does bank 1 do? It goes ahead and richens the mixture. What does that do for cylinder 1 and cylinder 5? Those cylinders are running incredibly rich now. So maybe we're fouling spark plugs on cylinder 1 and 5, all because we're trying to correct a condition that's on cylinder 3. So imagine a vehicle that's able to trim fuel for each cylinder individually. It's just going to make engines run so much more so much more efficiently. All right. So O2 sensor testing. You know, we had 62 different codes for O2 sensors. The computer is very, very good at testing oxygen sensors. Usually, oxygen sensor information is very, very well documented inside of live data on a scan tool. But really diagnosing O2 sensors using the code, criteria, and descriptions is just like diagnosing any other circuit. You can use a test light, DVOM, lab scope, anything like that. And live data is super useful for looking at oxygen sensors. You could even check a heater circuit code. You could use an amp clamp and see if you have current flowing for your heater circuit. And some scan tools, and depending on the vehicle, will actually include a heater PID labeling the amperage that the heater is taking. Now, those are for all the circuit codes, you know, high circuit, low circuit. that kind of thing. Slow response codes are the tricky ones, you know, they're just a whole nother animal. So this is where we come across this fine line in automotive diagnostics. You know, I'm always up here preaching to you guys, test, don't guess, you know. We don't want to be parts changers. So every manufacturer is different, right? Information can be vague or non-existent. So why test if we don't have all the info? Use your common sense, use automotive system knowledge. Here, let me show you guys what I mean. Here we have an 09 Impala 3.9, setting a P0133, bank 1, sensor 1, slow response. In order to just perform the test, in order for the computer to just run the test, it cannot have 46 of these other codes set. Okay? So before it even performs the test, all these other 46 codes cannot be in the computer. Then we have to make sure system voltage is correct. We got to make sure it's in park, not in park, reverse, or neutral. We got to make sure it's warmed up. We got another page of test conditions. The test conditions have to be met for 3 seconds. So it's got a lot of things to do just to run this test. Then we have the conditions for setting the DTC. The ECM detects that the HO2S1 rich to lean and lean to rich transition time takes longer than a calibrated value. What the heck good does that do me? What is a calibrated value? I'm not going to go ahead and spend the time hooking up a scope to this thing if I don't know what I'm testing for. If I don't know what this calibrated value is, why am I going to waste my time looking at a slow response code? As a technician, this is a waste of our precious time. But it gets better. Our O2 Mazda Tribute that's sitting over there is setting a P0136. It indicates the output voltage of the rear O2 sensor, bank 1, fails to meet the calibrated limits. Again, calibrated limits. What good does this do me as a technician? I don't know what a calibrated limit is. I went one step further. I went out to Ford's OBD2 theory and operation page because this is a Mazda 3-liter. It's the same as the Escape 3-liter. I pulled this info. It says voltage that can exceed the calibrated, voltages that exceed the calibrated rich and lean thresholds indicate a functional sensor. If the voltages have not exceeded the thresholds after a long period of vehicle operation, the air-fuel ratio may be forced rich or lean in an attempt to get the sensor to switch. So what is this telling me? This is telling me after the sensor hasn't responded for a long time, the computer is going to go ahead and force it rich, force it lean, and try and get it to get out of its threshold, okay? But again, long period of vehicle operation. What does that mean? 30 seconds, 30 minutes, 3 hours? I have no clue. Why am I going to spend the time hooking a scope up to this thing if I don't have the parameters or the specs of what I'm testing? So what am I trying to say here? We need to trust, but we can't be trusting blindly. We can't just be shotgunning parts at cars, guys. We have to have some faith in our PCM and its testing abilities. You know, why waste our precious time hooking up a scope to something, hooking up all this test equipment if we don't even have specs to test? You know, time is money. Now I'm going to show you guys on these vehicles what exactly I mean when we hook up these scopes and that kind of thing. But I guess the moral of the story here, guys, is that we need to have trust and faith in our PCM. It's performing 62 different tests just on our oxygen sensors. We need to trust that it's performing those tests properly, and we need to use common sense. Don't blindly trust, you know, verify the system's functioning properly, verify your fuel trims and there's nothing else going on in the system, and always, always, always read your code descriptions, circuit descriptions, and code set criteria. All right, so that's enough talking. Fuel trims number 3, widebands is going to be next month. Let's go over to the vehicle now. I think Fritz might be over there sleeping in the car, but let's go wake him up and play with the scope and play with some scan tool stuff on our GTO and on our Mazda. All right, let's go. All right, Fritz, you're not sleeping.
No, I took my nap already.
Okay, good. So, well, hopefully everybody else isn't sleeping. You know, that was a lot of information to talk about, but now we're to the fun part, right?
Yes, we are.
We get to play with the vehicles, we get to play with the tools. If you guys notice, I don't know if you all watched the Tech Connect episode that we had that time where we talked about getting a Pico scope, but you can see here in front of us in this nice big box, I got the Pico scope all set up on our GTO. And for those of you who aren't familiar, Pico scope is a laptop-based ignition scope, and it's kind of like the Cadillac of scopes, I guess. I love this thing. So we haven't had a lot of time to play with it yet, but I do have hooked up to the scope right now, bank 1, sensor 1, and bank 2, sensor 1 on our GTO. So I went ahead and back probed into the PCM on our GTO because it was easier to get to the PCM than it was to the oxygen sensors themselves. Why don't we fire it up and take a look at what they look like on the scope. Now, for those of you guys that did watch the last class, if you remember, our GTO's got some issues. It's running lean. So we haven't fixed the issues yet. It's still running lean, so let's see what these oxygen sensors look like.
You ready, Mike?
Go for it. All right. And right now we have them sitting right around the 0.2 or so millivolt mark, 0.2 volt mark, and as they heat up, we're going to start to see them move. There they go, they're starting to increase. And again, it takes a little bit of time for them to come up to temperature. And once they get hot, they should start switching. We're starting to see a little bit there out of our blue trace here. There they go. And we're on a 500 millisecond division. So 500 milliseconds per division down here. So we're looking at 5 seconds in total across their screen. And like I said, guys, I'm not too familiar with the picoscope yet, so if I do anything stupid or if there's an easier way to do something, please let me know. I'm always up to learn more about this thing. It's been a lot of fun so far. So here we have our sensors switching back and forth. They look relatively normal. I'm going to go ahead and zoom out here a little bit. We'll bring it out to 1 second per division. And you can see they are switching back and forth. They do seem maybe a little bit lazy, but we got to remember, this engine has problems right now. It is running lean, but our computer's gone ahead and it's done its field trim compensation. So why don't you go ahead and shut this off. Let's just leave the key on. All right, so hooked up to this thing right now is the good old GM Tech 2. The reason why I have the GM Tech 2 hooked up is because I couldn't find anywhere on the Snap-on scan tool of how to reset the field trims. On here, it's the push of a button. So unfortunately, I just accidentally unplugged it. So I'm going to go in, enter in all our vehicle's information in here. And that awesome sound right there. Yep. That's when the coolant temp sensor's disconnected. It makes that noise. All right, I'm going to go to special functions, and actually here, I'll put it up on the screen so you guys can see, hopefully. It's kind of hard to see because it's an old scan tool. So I'm going to go into field system and field trim reset. And it's going to wait for some data here. And I just want to note, guys, right here, long-term field trim, bank 1 and bank 2 are both at positive 25%, okay? So we're adding fuel. Now I'm going to go ahead and reset these. And what we're going to see is we're going to see our oxygen sensors respond, and we're going to see our field trims respond. So I'm going to push the reset button, and there they go. We're back to 0. Okay, we're going to exit out of here. You want to get the Varus hooked up, Fritz?
Sure.
So what we're going to do now is, once the Varus is all hooked up, I'm going to go ahead and I'm going to bring up the bank 1 and bank 2 field trims, long-term and short-term, up on the scan tool, and we're going to look at the lab scope graph at the same time. So we're going to have them both up on the screen so that you guys can see when this engine starts up, it's going to be running incredibly lean, right? Because our long terms haven't adapted to this yet. They're at 0. So we're going to see our short terms ratchet up, just like we saw in that graph that I had made. And then eventually, once our short terms ratchet up high enough, our oxygen sensor is going to swing up and switch. And at that point, then we should see our long-term field trims start to adapt. So I'm going to go to data display here, and hopefully we have communication. Excellent, we're in. So I'm going to bring up a custom page here again. I'm going to deselect all, and I'm just going to grab our 4 sets of field trims and throw them into graph view. Now, it is important to note, guys, that with the scan tool here, we are sitting at a 0 in the center line and a 1 and a -1 on all 4. This will auto-adjust as the trims start to move once the vehicle's been running. So why don't we get the scope up on the screen, and let's get the scan tool up on the screen at the same time. Let's fire this thing up, and let's see what happens. Go for it, Fritz. So it is going to take a second again to get into closed loop. Remember, the sensors have to be hot and responding to get into closed loop. And I'm going to zoom this back into where I was before at 500 milliseconds. There we go. And you can see our short terms haven't started responding yet. We're running just straight lean right now. Our engine's running super lean. We have an excess of oxygen across our O2 sensor. And there we go. Our short terms are starting to move. They're increasing, increasing, increasing. Our long terms have already started to adjust. So this thing's working really fast. And there we go. There's our switch. At that point, when that switched, is when our oxygen sensor switched. And now we see our short terms starting to come back down again. So our long terms have ratcheted up, and our short terms are coming back down to their happy point. Remember guys, the whole point of long-term fuel trims is to go ahead and make those short-term fuel trims happy. So here we're at a positive 25 on our long terms, and our short terms are hovering right around that 0 mark. And look, our oxygen sensor's happy again. It's back to switching like it's supposed to be. All right. You want to just shut it off for a second, Fritz?
Sure.
Now I want to add in one more aspect here. So up on the screen there, guys, we had, what did we have? We had our input, right, our oxygen sensor, and we had our processing, right, the fuel trims. So we can actually add in one more item here. Let's add in the output. Let's add in the pulse width of the fuel injector. So what I'm going to do is I'm going to go on the scope here. I'm going to turn on our channel C, and I need to tell channel C that I have a 10-to-1 attenuator on here, because when you're scoping this fuel injector, you can get a spike that's over 100 volts. So we want to protect our scope. So we're using this attenuator on here to protect the scope. So I have it set up. I've told it that I'm using a ×10 probe or a 10-to-1 attenuator. You could use either. ×10 just gives me the option to have a bigger voltage range. So I'm going to go ahead and select +50. And now I'm going to zoom this thing way in, because I want to see our fuel injector on time, okay? I want to see the milliseconds of our fuel injector. And from scan tool data, we know that injectors pulse, really, really low in the milliseconds. So we want to definitely zoom in our graph here to get down to the milliseconds per division so that we can see our injector pulse. So I'm going to bring it down. Let's start with 10. I'm going to add in some active filtering on our oxygen sensors, try and clean those lines up a little. They're a little fuzzy looking. All right, let's see what this looks like, Fritz. Go ahead and fire this thing back up. Okay, so we have that. I'm going to bring it in one step further. Let's take it down to 5. Perfect. I'm going to throw on a trigger on channel C, and there we go. Okay. So right here, what we're looking at right in here is the pulse width of our injector. So our injector's steady, our computer turns the injector on, and it sprays for this amount of time, and then it shuts it off. All right, so I'm going to measure that amount of on time of the injector. And actually, I'm going to take the mouse wheel. What's nice about this scope is that I can take the mouse wheel here, and I can go ahead and zoom this in really easily. So I'm going to throw some cursors up here, and it's going to automatically measure the on time of our injector. And I'm going to try and get it right to where it's happy spot here. And remember, guys, with short-term fuel trims, it's always going to be adjusting that pulse width of that injector to run it rich and to run it lean. So I want to just try and find that happy spot in here. And I think we're pretty close here. So I would call this injector right now at about a let's just call it a 3 millisecond on time, right? 3.073, 3 millisecond on time, okay? And if we go ahead and zoom back out, what I want to watch now, you can see our oxygen sensors keep moving up and down here, and that's their switching from rich to lean, but we're zoomed in so far that it is hard to see. Now if we zoom this back out, we might get a little bit more of the waves. There we go. We got some more of the waves. But so this is exactly what's happening on this engine right now. Ooh, it sounds like she wants to stumble out there and die. Look at that. They just went completely lean. All right, I'm going to bring it back to 5 milliseconds so we can watch this. Now what I'm going to do, guys, is, oh, our CO alarm's going off. That beeping is just our CO alarm. That just is to keep us safe so that Fritz and I don't croak when we're on camera. So it might kick our fan in here, but it's not a big deal. All right, what I got here, guys, is a good old can of brake cleaner. I'm going to force this thing to run rich. Be careful whenever you're using brake cleaner anywhere near the engine, because it's added fuel. You know, if you have an ignition problem, you could create a spark in the engine and you could start a fire. So be careful. What's the trick that you had, Fritz?
Well, if you, sometimes the injectors make so much noise, you know if you got an arcing going on.
Sure.
If you're not sure, if you believe you got an arc, get a little bottle of water with some salt in it.
Okay.
A sprayer, shake it real good. and spray it over. That'll make that spark jump. And if you do not spray anything.
Yeah, exactly. Don't put any fuel in there. Now, personally myself, I started an engine on fire looking for a vacuum leak one time.
I guess once in a while we do have a little problem.
Yeah, so just be careful. So what I'm going to do is spray this right into our vacuum leak, and we're going to add fuel to the system. Now what we're going to see is if we go back to our lab scope here, what we're going to see is we are going to see our oxygen sensors go rich, right? They're going to go right around that 0.9 mark, and they're going to stay there as long as I add fuel. Now Dave, can you go ahead and bring up the scan tool on here as well? We're going to see our short-term fuel trims start to react as well. We're going to see them drop down, right? Because they have to take fuel away because we just added a whole bunch. And then our long terms are going to react, and we're going to see our pulse width of our injector react. So I'm going to zoom this in again so that we can have a nice easy picture to see. And so we're right about there. We'll call that 3 milliseconds. And here we go. I'm going to start spraying. And there she goes. She's running rich. And look at our pulse width of our injector, it's dropping. Look at our short-term fuel trims, they're dropping. We're trying to lean this engine out, right? We're trying to cut back on the amount of fuel going into the engine right now. We're trying to lean it out. Look at our long terms react. This thing is running rich, but look now, our oxygen sensors are pegged lean. Because I took that fuel away now, the oxygen sensors have responded, the short terms and long terms have responded, but they're not fast enough. This thing's running lean until our fuel trims start to react, and we'll see our sensors go back to switching. And look, our pulse width of our injectors right back to where we were before. So I'm just going to do that again. I'm going to add fuel. We're going to see them stay rich. Now they're not switching at all. And look at our short terms drop. Our long terms will respond. And then I took the fuel away now, and these things will go back and they'll sit lean now because the short terms aren't adding enough in there. All right, you can go ahead and shut this thing off, Fritz. So again, that's the inputs, the processing, and the outputs. It kicked our fan on, so Fritz and I can breathe easy now.
There you go.
So that's our inputs, our processing, and our outputs. You know, it's really cool to see all this stuff in action, and I hope you guys enjoyed being able to see that. So Fritz, why don't we bump over to the Mazda now? If you want to get the Veris hooked up to the Mazda,
sure.
I'm going to look to see the comments that you guys have sent in here and see what we got. Oh, wow. Holy cow. Look at this, guys. Jeez.
Got a ton of them.
This is the most comments I've ever seen from you guys. This is awesome. All right, we're going to start at the top. Let's go with the t-shirt question first. So the question was, if you're installing a new oxygen sensor, fill the connector up with dielectric grease. It seems like all of you guys knew that because you said D for neither, so that's correct. Again, we talked about that just before. Do not put dielectric grease in that connector. And Technician B is looking at scan tool, graph data, says it's constant around 500 millivolts. He says it's failed, so he wants to put a new sensor in. He's incorrect also. That bank 2 sensor should remain pretty constant. Now we got a lot of answer D out there. Tom Couch, James Erickson, Mike, Nick, George, Thomas, Jeff, Terry, Jeff again. You know, Jeff, the more times you say D doesn't mean more t-shirts. You're still only getting one, sorry. We got William out there saying D, so a lot of you guys knew the answer. I'm shocked, that's awesome. That's really, really good. See, I was always one, I wanted to install dielectric grease into connectors, but now we know we're not supposed to do that, right? So all you guys who answered it correctly, if you want to bring up my email address on the screen, go ahead and send me out an email with your t-shirt size, your mailing address, and the color of the t-shirt that you want, and I will make sure to get a shirt out to you as soon as possible. And Tam Couch, I did just send your t-shirt all the way to the UK, so you should be seeing that thing soon. What else we got for comments? A whole bunch of stuff. Volvo had many firsts. He said D because the cat's probably okay, that's true. Downstream should be steady, nice. We got a Spanish comment here, Fritz.
What's that?
We got a Spanish comment here. I think he might be asking about the video in Espanol.
And who's that? Oh, Oscar Avila. He says, we appreciate, thank you.
All right, and the video in Spanish is going to be in 2 weeks on Wednesday.
Yes, that's right. En 2 semanas, el miércoles, Oscar, vamos a tener el video en español.
All right, and then James came on asking about those 2 white wires on the oxygen sensor. You know, I'm going to talk with an engineer about that to see if polarity matters, maybe with the heat up time or something. My gut kind of says no, but check back in the Tech Connect episode. I'm going to definitely answer that question. Now, I can't go through all of these. I will take the time to go through them after the broadcast today, but I'm not going to do it live because I've already taken a lot of your time, and I still want to look at another vehicle. We do have this Mazda sitting here behind me, so I'm going to go through all these, and any questions or comments I will bring up in the Tech Connect. So make sure you guys join us for that next Tech Connect. All right, Fritz, you got this hooked up? We good to go?
Ready to go.
All right, this one's going to be fast, I promise. So I'm going to get our scan tool hooked up here onto our O2 Mazda. And we're going to go through this way. We got a Tribute here, VIN 9, 3 liter. All right, and you got the K20 key on there?
Yep, let me turn the key on for you real quick.
Engine, and the key's on.
And you're ready to go.
Just heard the key turn on. And let's just pull codes quick. So like I said, this thing has a P0136 in it, and there it is, P0136, oxygen sensor, bank 1, sensor 2 circuit fault. All right, so that's going to be our post-cat oxygen sensor. This is a sensor that should remain relatively steady. If we want, we can just quickly look at data. Actually, I want to look at our freeze frames first, but I didn't expect to look at these, so I apparently don't know where I'm going. Actually, I know where I'm going. Let's go into generic functions. We can look at freeze frame through generic functions. I just want to see when this sensor had failed, right? We want to be able to try and duplicate that concern. So what do we get for freeze frame data? We get some engine RPM, we get some fuel trims, some vehicle speed, calculated load, engine temp, open loop. So this thing made it go into open loop. You see our fuel trims are pretty bad right here, right? So bank 1 and bank 2 short terms are relatively high, so this thing was running slightly lean, and our load and our speed. So again, this test here for this 136 has a lot of different variables. Now what I would do is I would go ahead and look at engine data, right? I already got the scan tool hooked up. I'm looking at this P0136. Next thing, let's bring up some live data. Let's graph some live data and see how the sensor reacts. So that's what I'm going to do. I'm going to go data, O2 sensors. And as soon as it loads here, I'm going to bring up a custom graph. Let's take everything out of there. All I want to see right now is just the millivolts on my O2 sensors. There we go. Okay. So we have oxygen sensor bank 1, sensor 2, oxygen sensor bank 2, sensor 2, bank 1, sensor 1, and bank 2, sensor 1. So these two on the bottom are going to be our fast switching sensors, and the ones on the top should remain relatively steady. So why don't we go ahead and fire this thing up, Fritz, and let's take a look at what we got. Again, our scales are going to adjust here once these things start moving. We just got to give them a second to warm up. Now I did have these engines warmed up before the class, but over the last hour they've cooled themselves down a little bit. And already we're seeing them respond. The benefits of a heated oxygen sensor. So our bank 1 sensors are switching already. You can see them going back and forth. Looking really, really nice there. And it looks like it's just going to take a minute here for our bank 2 sensors to come online, because right now they're only reading 3 millivolts. So I'm going to go ahead, I'm going to bring up the RPM a little bit and try and warm these up a little faster. There we go. And now we got a sensor responding. All right, so we can see bank 2 sensor 2 is starting to respond, right? It's growing in voltage. It's getting right up, it's around 500 millivolts, 600 millivolts. And it's pretty steady. We don't see it switching at all, right? But our bank 1 sensor 2 here is actually responding now. Wonderful. You can see for a while here it wasn't responding, and now it's actually online, of course. And there it goes. All right, so this sensor here has an intermittent problem inside of it. It's not functioning all the time. We're actually able to see this thing act up. To be honest with you guys, I was never able to get this sensor to actually react, but we can see here that it is working a little bit. If you look at our graph here, we actually dropped back down to 0, and then we're back up to where we need to be. So what I wanted to talk about here was just that we need to verify that that sensor is actually reading 0, not that we have a wiring issue or a PCM issue. Easiest way to do that, just throw a voltmeter on it, right? Easy to get to, only have 2 wires to hook up. So I'm hooked into the signal wire, which would be like the gray wire and the black wire for ground with my voltmeter. And I'm just gonna watch the voltmeter in comparison to what we have on our graph. Now it's not gonna be nearly as fast as what the computers or as what a scope is, but it's a good way to just see if our sensor's putting out voltage or not. And what's nice about this meter that we got here, this 233, is if I'm looking at this thing in the car, I can leave this part sit under the hood, and I got our screen right here. So you can see our sensor is kind of, voltage output's kind of low here, right, compared to what our scan tool's doing. And it might be because my back probes have fallen out. Let me take a look here. And this sensor was kind of easy to get to. In fact, Dave, can you bring up the picture of this sensor for me? You guys can see up on the screen there, I'm back probing in this sensor and we already have an issue with it, right? Look at what it's all covered in. It's covered in oil. That is a problem. All right, yes, I had my back probes not in far enough. There we go. So you can see we're right around, following the scan tool pretty well. But again, when I was testing this thing this morning, when I was testing it yesterday, this sensor was completely unresponsive, just reading 0 volts consistently. And we are super, super low in voltage here. Now we could go ahead and fluctuate our RPM and try and make our rear O2 sensor switch. And you can see we're dropping out now on this sensor. We're reading back down to 0 volts, but that's responding. And you can see our bank 2 sensor 2 is responding nicely. So by a little bit of RPM manipulation, you can make your rear O2 sensor switch because the cat's just not able to react fast enough, right?
That's right.
All right. I think we can shut it off.
Sure.
You know, that's just an easy way to go ahead and just make sure that you don't have a wiring issue or a PCM issue. You know, you got 6 feet of wire between the sensor and the PCM. It goes past exhaust. It might get hot, melted, corroded, you know, anything like that. Just throw a voltmeter on it. Check to make sure you got a voltage output. All right, I think I've talked long enough. What do you think?
Yeah, I got a sore throat from watching you talk.
Yeah, from watching me talk. Nice. Okay, guys. I apologize again for the 11 o'clock class. We had our technical difficulties, unfortunately. I appreciate all you guys who normally come to the 11 o'clock class. Appreciate you being here for this one, taking time out of your afternoon. Sorry for taking up a lot of your afternoon, but I wanted to get all this information out in one class because I feel like it would just be, that month in between would just be too much to be able to get back into this and get back right on the same page. And now we're closer to talking about widebands, right?
Yes.
So March, I believe it's March 2nd, if I remember right, testing my memory here. March 2nd, we're going to be talking about those wideband sensors, air-fuel ratio sensors, and that kind of thing. So make sure to join us for that. Crossing my fingers, we'll have that 11 o'clock class. You know, things come up. So I just want to take one quick last look at our comments here. Just see if anything else came up that I got to address quick. Yes, Corey Davis is using a filter will clean up those scope patterns. I don't know if you said that before or after I threw the filter on, but you can do that right through here, throwing in a low pass filter. We can see that, clean up that scope pattern. All right, excellent video, awesome. What color shirts do you have? James, we have blue, we have gray, and we have black. Let me go grab those quick. Hang on one second. All right. Here we have our blue shirt and black and gray. So if you guys got the question right, again, you want to just throw my email back up on the screen there. Email me with your t-shirt size, mailing address, color of the shirt if you answered the question correctly. And I think that's about it. Mm-hmm. Did you have anything else?
No, actually no.
All right.
Covered a lot.
Here's my little disclaimer. Be careful if you're ever spraying brake clean or anything flammable under the hood of your car, okay? I don't want to hear any stories of anybody running into any problems, okay? So I know I did it in this video, but I verified everything was okay beforehand and was careful about it. So be extra, extra careful if you're using any sort of external fuel source. All right. So guys, I think that's about it for today.
Yes, that's it.
All right. So thank you for sticking with me all this time. And I hope you guys learned something today. And we'll see you guys again next time in the Wells Tech Garage. Thank you. A couple more technical difficulties. All right. Thanks, guys. And we're out. We'll see you guys next month.